Hello, Math 201. Welcome to today's lecture where we're going to go back and cover section 4.2, the mean value theorem. So this lecture will be a little bit different than most because it'll be kind of more, how do I say it, theoretical in the sense that we're going to talk about these theorems that are actually really, really important to the bedrock of calculus. So there'll be some proofs and some fun ideas. And so it won't be super applicable to like real world applications, but just kind of the theory of calculus, some really beautiful and cool ideas. And so if you like this, then awesome. If not, it's still useful stuff and we'll use it later, but that's kind of the flavor. So the mean value theorem is a super important theorem in calculus. In order to get to it, we're going to do a kind of more specialized version of it, which is called Rolle's theorem. And again, and to kind of get the idea motivated for Rolle's theorem, let's look at this picture. So the idea is we start with a continuous function that is differentiable. So there's no hard points on it. And the endpoints, so it's on a closed interval from A to B. And on the endpoints, it has the same value. So same value there, same value there. Then Rolle's theorem tells us that there must be some point, in this case C, where the tangent line at C, which is the derivative, so f prime of C is equal to 0. So it has a horizontal tangent line at some point. If you meet the following criterion, you have a closed interval where the endpoints have the same value. And so it can go up, it could go down, it could do something like that. But there's some point, there's going to exist some point where you have a horizontal tangent line. That's the idea of Rolle's theorem. And the reason is this, because as you're kind of moving in a continuous differentiable way, you have to start and end at the same place. So there has to be some kind of local extrema going on, right? If you start and end at the same place, there has to be some sort of local extrema happening. And so at that local extrema, there's a flat or horizontal tangent line. That's the idea of Rolle's theorem. Or if you start and end at the same place and the absolute extrema are at the both endpoints, then you have a constant function. Those are really the only cases. Or it could do something crazy like that, but you're going to have lots of horizontal tangent lines in those cases. And so that's the idea of Rolle's theorem. So let's record it. So let f be a continuous function on a closed interval and differentiable. So it doesn't have to be differentiable at the endpoints. It just needs to be differentiable on the interior. It's a minor point, but you need the endpoints to be the same. So if the endpoints are the same, then there is at least one point, some interior point that has derivative 0. And so that's this picture. And the proof is actually not that bad. The idea is that the function, because it is continuous and differentiable, it is going to satisfy the extreme value theorem, which means it has an absolute max and an absolute min on the closed interval. And those values are either attained at an endpoint or an interior point. So going back to this picture, if we have the function endpoints and the function is continuous and differentiable, it must attain an absolute max and an absolute min. In this case, the absolute min is there and there, and the absolute max is up here. If the absolute max and min both occur on the endpoints, then it has to be a constant function, right? And that's case one. So suppose both absolute extrema occur at the endpoints, then this is the absolute max and this is the absolute max, and they're both the min. And because this is a continuous differential function, that means it has to be continuous. It's just a continuous function. And because the endpoints are the same, then it's just a constant function. And so f is constant, and that means the derivative is 0 everywhere, right? So for all C on the interior, and so it meets it. The other possibility is that our absolute extrema, either a max or a min, occurs somewhere in the middle. And so if it occurs at some interior point, then this absolute extreme must be a local one, right? Because if it's an absolute, either an absolute max or an absolute min on the interior, because of the fact that it's continuous and differentiable, it had to continuously go up to that point and back down to that point in order for that to be an absolute extreme. And same for this to be an absolute min, it had to go down and back. And so that means that these are local extrema. And because these are local extrema, that means that there's going to be a horizontal tangent there, right? Because at a local extrema, you have the slope, the tangent slope of the tangent line. Sorry, that's an ugly picture. The slope of the tangent line is 0. And that's from theorem 4.2 in our last section, 4.3. And so that's the idea, is that if the interior has the absolute max, the absolute min, then at that point, that had to have a horizontal tangent line. And obviously you could have more, there could be more bumps in here, but at the absolute one, you're going to have it be local. And so there has to be a horizontal tangent line. And so that's Rolle's theorem. So Rolle's theorem guarantees that we're going to have some point where the derivative is 0. And here's a huge warning. We need continuity and differentiable. Here are 2 examples of functions that have the same value at the endpoints, but do not satisfy Rolle's theorem. Here's one because it's not continuous. So because this is not a continuous function, there is no place where there's a horizontal tangent. No horizontal tangent lines anywhere here. Or you can have it where it's not differentiable. So it goes up and it goes up to this kind of point, a cusp, and there's no horizontal tangent because the function's not differentiable at the max. And so you need continuity and you need differentiable for this to work. And then here's a classic example of what we can do with Rolle's theorem. So verifying Rolle's theorem, find an interval on which Rolle's theorem applies to a given function, then find all points at which the derivative is 0. And so let's factor this function. So if you pull out an x, what are we left with? We're left with x squared minus 7x plus 10. Factoring that further, we get x minus 2 times x minus 5. And so this is the function x times x minus 2 times x minus 5. So at 0, 2, and 5, the function is 0. And so f of x equals 0 when x equals 0, 2, or 5. And so we could pick any of those, any combination of those to be our endpoints, because that means it's going to have the same function value. But in particular, f of 0 equals f of 5 equals 0. And so let I be the interior of that interval, which is 0, 5. So we want to find the value c for which f prime of c equals 0 in this interval. And by Rolle's theorem, it has to exist because the endpoints are both 0. And so there must be somewhere where there's a critical point, right? Where the derivative is 0 somewhere in here. And so let's find it. So what is f prime of x? Well, f prime of x is 3x squared minus 14x plus 10. And we want to set it equal to 0. And what do we get? Let's just do the quadratic formula. X equals 14 plus or minus the square root of b squared, which is 14 squared, which is 256. Whoops. 256 minus 4ac, which is 4 times 3 times 10, all over 2a, which is 6. So you get 14 plus or minus the square root, 120, so 136 over 6. And so I have no clue what those values are. Square root of 136 is roughly, so this is where I would just get a little like phone calculator and just see what that roughly is. Square root of 136 is roughly 11.66. So if we plus 14 and divide by 6, so this is roughly 4.277. Or if we subtract, so 14 minus that, so minus 14, and then divided by 6, or 0.390. So those are our two values, 4.277 and 0.390. If this was an exam, I would pick nicer numbers that you could actually factor, but for those purposes. And so this one and this one both satisfy Rolle's theorem because they're both in here. And so C equals 0.390 and 4.277 are both in the interval 0, 5. And so those ones are the ones that are guaranteed by Rolle's theorem. And here's kind of a picture of that. Oh, did I mess this up? They got slightly different numbers than me. What did I do wrong? 120, 12 times 10 is 120. Square root 256. Is that what 14 squared is? I thought 14 squared is 256. 196. Oh, whoops. That's where I messed up. Whoops. That's 196. And so this is actually square root of 76. Whoops. And so this is actually, sorry about that. This is going to be 0.88, comma 3.79. So even I'm fallible, but that's the idea. And so those are the 2 points that are going to be between 0 and 5. So because the function is 0 at 0, 2, and 5, we know we're going to have, by Rolle's theorem, some values in between those points where the derivative is 0. And those are critical points. And so that's Rolle's theorem. And now we're going to use Rolle's theorem to prove the main theorem, which is the mean value theorem. And again, the best thing to do here is a picture. The picture is this. If you have some continuous differentiable function between, on a closed interval, so from A to B, so continuous differentiable, then the idea is that the slope of the secant line, the slope of the line between the two endpoints, which, remember, the slope of this green line right here is y, which is f of b minus f of a, so y2 minus y1 over x2 minus x1. So this is the slope of the secant line. F of b minus f of a all over b minus a, that's the slope of this line. There is some point on this function whose tangent line has to be parallel to that line, right? So if we took his tangent line, that tangent line is not parallel. This one's closer, and then eventually you will get to one where they are exactly parallel. And that is the idea of the mean value theorem, is that because the secant line is kind of the line connecting these two, and it goes up, and the tangent lines are going to be bigger, equal, and then smaller. And so because in order to get back to the secant line, the tangent lines kind of had to change until one of them has to pass through, and then they'll change back. And so that's the idea of the mean value theorem, is that there is some point in between A and B, some point C, that has the tangent line slope equal to the secant line slope, which, written in terms of the derivative, is saying that f of b minus f of a over b minus a is equal to f prime of c. Another way to say this is that this is kind of the average rate of change, right? If you want to know what the average rate of change between two things is, that's the secant line. And it's saying that there is some of the rates of change are going to be bigger than it. Some of the rates of change are going to be smaller than it. And there's going to be some place where the average rate of change is equal to the instantaneous rate of change, which is what this is. And so that's what the mean value theorem is. And so recorded, if f is continuous and differentiable on the given interval AB, then there's at least one point such that the slope of the secant line, which is f of b minus f of a over b minus a, is equal to the slope of the derivative. And the proof of this, I'll give a sketch, is really actually just a clever use of Rolle's theorem. And the idea is this: we call this line right here, this secant line, we're going to call that L of x. And then this line and this function, the difference between them, f of x, is going to be a new function. We're going to call their difference g of x. And we notice that their difference is 0 at a and b. And so it has the same value at a and b. And therefore, it's going to satisfy Rolle's theorem. And so let's record that. So let L of x be the equation of the secant line, and then set g of x to be the function f of x minus L of x. Then we notice that if you plug in b right here, that the function and the secant line have the same value. And if you plug in a right here, the function and the secant line have the same value. So that means their g of b and a are both 0. And g of x, this function right here, is continuous and differentiable because this one is continuous and that's continuous and differentiable. So if you take their difference, it's continuous and differentiable. And so we can apply Rolle's theorem. And so here's the picture. G of x is f of x minus L of x. The difference between this, so it takes the value of that, right? So here it's 0, here it's some positive number, and then 0. And the idea is that because that value equals that value, that g of b equals g of a, then by Rolle's theorem, there is some c in the interval, in the interior, such that the derivative of g is equal to 0, right? That's Rolle's theorem. So this function g, which is just f of x minus L of x, has to have derivative 0 at some point. But what is the derivative? The derivative g prime of c is just f prime of c minus L prime of c, right? If you take the derivative of this function right here, the derivative, you just take the prime of everything and then you plug in c everywhere. And so you get g prime of c equals f prime of c minus L prime of c. But what is L prime of c? That is the slope of the secant line, right? Because L is the secant line. And so L prime of c is just the slope of the secant line. And so if their difference is 0, then solving, you get f prime of c equals L prime of c. But L prime of c is just the slope of the secant line, which is f of b minus f of a. And we're done. And so that's the mean value theorem, is that there is some value right here, some c value, such that the slope of the tangent line there is the same as the slope of the secant line. Or put in terms of instantaneous rate of change and average rate of change, the instantaneous rate of change right there is equal to the average rate of change on the interval. And so now let's do an application of that. Let's use it. So determine whether the function satisfies the conditions of mean value theorem on the interval. If so, find the points guaranteed to exist by the theorem. So in order to satisfy the conditions, it needs to be continuous and differentiable on this interval. And that's fine. It's a polynomial, right? So f of x is a polynomial. So it is continuous and differentiable everywhere. Continuous and differentiable everywhere. So that's fine. So it satisfies that. Slope of the secant line. Slope of secant line is going to be the following. It's going to be f of b, so f of 2 minus f of a, which is f of negative 2, all over 2 minus negative 2. What is f of 2? So f of 2 would be 16 minus 6 plus 1. Minus f of negative 2 would be negative 16 plus 6 plus 1 all over 2, 4. And so what's the slope of the secant line going to be? It will be 11 plus 9 over 4, which is 5. So that's the slope of the secant line. And so it satisfies the theorem. So satisfies mean value theorem because it's continuous and differential everywhere. So there is C in the interval negative 2 to 2 such that f prime of c equals the slope of the tangent line, which is 5. And so how do we find that? So what is f prime of x? So set f prime of x equal to 5 and solve. So set f prime of x equal to 5 and solve. So what is f prime of x? It will be, so f of x is 2x cubed minus 3x plus 1. And so the derivative will be what? 6x squared minus 3. So f prime of x equals 6x squared minus 3, set equal to 5. And so you get x squared equals 8 over 6. And so x equals plus or minus the square root of 4/3. And so those are the two values. And so the one that will be guaranteed, so both of those values are going to be guaranteed to have slope equaling 5. And so here's the picture of that. So which is roughly plus or minus 1.15. And so we see that this function goes up and down. Its average rate of change is that green line right there, the slope of that green line. And so there are 2 points, that mean value theorem, where it's going to have slope 5. Slope 5 there, slope 5 there. All right. The last thing we're going to do is just some kind of quick, fun which I think are fun. Consequences of the mean value theorem. One important one: if a function is differentiable and its derivative is always 0 at any point on an open interval, then that actually implies that the function has to be a constant function. And this really follows very quickly from the mean value theorem, because if a, b is any interval, any sub-interval in I, right, just pick 2 points in I, then that's an open interval. And by mean value theorem, there's going to be some c in that open interval such that the slope of the secant line, which is f of b minus f of a over b minus a, is going to equal f prime of c. But f prime of c is 0 because every one has derivative of 0 here. But this is true for any interval a, b, and I. And so that means f of b minus f of a over b minus a equals 0 for any a and b. But if you just multiply b minus a over to the other side, then that means f of b minus f of a equals 0. And this is true. And so then f of b equals f of a. But this is true for any interval a, b, where a is not equal to b and I. And so that means that f of b equals f of a whenever a is not b in this interval. But that means it's a constant function. So we're done. And so if your derivative is always 0, then you actually have to be a constant function, which is really important and is especially important for this next result, which is saying that when functions have equal derivatives, if their derivatives are the same, then they differ by a constant. And this will be really important when we talk about integration later. But the idea is that if two functions have the property that their derivatives are the same for all x in an open interval, then it turns out that their difference is a constant. And so f and g differ by a constant, and the proof is really straightforward. It follows from the theorem above. F prime of x minus g prime of x is 0, right? Because if f prime of x equals g prime of x, then their difference in derivative is 0. And so if the derivative, but this is just equal to f minus g. This is the derivative of their difference, right? Because derivatives are linear. And so this is going to be f minus g prime of x. And so this function, f minus g, has derivative 0 for all x. And so we can apply this theorem up here, right? The derivative is always 0. And so we apply theorem 4.5. And so that means f minus g of x is a constant function. But if this is a constant function, then that means they differ by a constant, and we're done. And so that's actually a really cool, important theorem too. It's a really quick, immediate consequence of the mean value theorem. All right, that should be everything you need to get the homework going, and I'll see you guys next time. All right, take care.